Let's talk about what is absolutely the most shocking subject on the FAA power plant exam, and that is electricity. Oh, I'm sorry, I know. That's absolutely volting. Well, it's a good thing I didn't do it twice. That's all I can say. Then the second time it becomes revolting. Oh, I'm sorry. All right, let's talk about it. What is the aircraft electrical wire size system of measurement? In the United States, it's the American Wire Gauge System. It tells you how big wire is, and that's how we measure wire in the United States according to the American Wire Gauge System. All right, now they coat aircraft copper electrical wire. What's it coated with? The answer is it's coated with tin, silver, or nickel. And why? In order to prevent oxidation. So you need to know that for the test. The electrical wire is coated with those things to prevent oxidation. Now, as a general rule, you're going to find that small terminals use insulation on the terminal, but electrical wires larger than 10 gauge do not have insulated terminals. They use uninsulated terminals. Now, actually, what you do in real life is after the terminal is crimped in place, you put a piece of vinyl tubing over the barrel and then lace that in place with lacing cords. So you put an insulator on the terminal yourself. All right, now let's assume you're installing parallel electrical wires in an installation and it's near a compass. What do you do to prevent creating a magnetic field? And the answer is you twist those on installation in the vicinity of a magnetic compass, and that prevents having a magnetic field. All right, another thing that you need to know if you're installing electrical wiring parallel to a fuel line, the wiring should always be above the fuel line. Why should it be above the fuel line? Because fuel won't drip up. Unless you fly inverted a lot, that's why. All right, what is the maximum allowable voltage drop between the generator and a bus bar? The answer is 2% of the regulated voltage. By the way, it has to do with power output of the generator or battery, but this is the FAA answer. The voltage drop of maximum allowable between the generator and the bus bar is 2% of the regulated voltage. Let's you and I take a real close look at an electrical connector, and let's talk about how electrical connectors are designed. First of all, most electrical connectors have a pin side and a receptacle side, and of course the pins fit inside the receptacle. Now, one of the things the FAA wants you to know is it is better to make the receptacle side hot, not the pin side. The pin side should be on the ground side of the connection, the FAA says, and the reason is this. If the pins are hot, they could easily come in contact with something and be shorted out. That's less likely when you're talking about the receptacle side. So the receptacle side should be the hot side, the pin should be the ground side. So in order to reduce the possibility of shorting or grounding when the connector is separated, AN and MS and all electrical type connectors used on airplanes should be installed with the pin section on the ground side of the circuit. Now, let's assume that you're trying to put a high-tension ignition cable in a rigid ignition manifold, and you're trying to pull these wires through. How do you pull them through the conduit without creating damage to these cables? And the answer is you dust them with powdered soapstone, and that way you can pull cables through a conduit and they'll slide through. Why? Soapstone is slick, and so powdered soapstone, sometimes called soapstone talc, and you can pull it through and leave it there because it does not damage the insulation, and it's non-corrosive and it's non-conductive. It's a great thing. Now let's take a look at Figure 4. We're going to use Figure 4 to determine the minimum wire size that you can use when you're installing some kind of electrical device. And they're going to give us some information first of all, so let's take a look at the information they're going to give us. They're going to say that first of all, the current required for continuous operation is 11 amps, so we have to be able to carry 11 amps of current. The cable length is 45 feet, the system voltage is 28 volts, and the maximum voltage drop is 1 volt. And by the way, this cable, we're going to use cable in conduit and bundles. Now, with that information, let's determine the minimum wire size. The question is, what's the minimum size copper electrical cable that may be selected? First of all, we need to determine the wire size based on voltage drop. And to do that, let's take a look at the chart and go to the left-hand side and notice there's several columns. We're looking for 28 volts. There's 28 volts. And if you go down at the bottom, we're also looking for a maximum of 1 volt voltage drop. And there it is down here. It's the one here. So it's this column right here. Now, our wire length was 45 feet. So if you go on the left, you see that this is wire length, and here's 40 feet, here's 50 feet. We're going to have to interpolate. Of course, they didn't give us 45 feet. So we make a line for 45 feet. Now, we're also going to use these diagonal lines for amperes. Here's 10 amperes, here's 15 amperes. What are we looking for? We're looking for 11 amperes. Once again, we're going to have to make our own line. They don't do anything nice for us and give us something easy. So we'll make our own diagonal line here for 11 amperes. And where these two lines intersect, we'll stop and make a dot. We'll read right straight down from that dot and get the minimum size wire we can use based on voltage drop, and we get in between number 14 or number 12 wire. That's what they call these on the test. A lot of mechanics call this 14 gauge wire or 12 gauge wire. But on the test, they'll call it number 12 wire and number 14 wire. But we get in between 14 and 12. The 12 gauge is a bigger wire, so we'll use 12 gauge because you always have to have the larger wire. And so based on voltage drop, we're going to use 12 gauge wire. But hold the phone. We're not done. We need to determine the wire size based on overheating.
And that's where the chart changes, right? So he's going to show us the old chart. For us, if you really want to do the overheating, you go to the wire and bundles one, which is more complicated. But we'll let him play through.
Do that. Let's take a look at these boxes in the lower right-hand corner, because there are three curves we could use based on overheating. Curve number 1 is for a continuous rating in amperes when the cables are in conduit and bundles. Number 2 is continuous rating in amperes when you have a single cable in free air. And number 3 is intermittent rating in amperes when you have a maximum of 2 minutes. The heating requirements or the cooling requirements are much higher on number 1, so it's going to force us to a bigger wire size. Now let's take a look at this and see if we can solve the problem. First of all, we're going to use curve number 1, and we're going to use the 11 ampere line that we drew in earlier. And when those two intersect, let you and I stop and make a dot. And all we have to do is read right straight down from that dot, curve 1 and 11 amperes, read right straight down and see what size wire we're going to use. It's between 18 gauge and 16 gauge. We're going to use the bigger wire. So based on overheating, it would be the 16 gauge wire. So which do we choose, 12 or 16 gauge wire? Well, based on overheating, it was 16 gauge. Based on voltage drop, it was 12 gauge. We're going to choose the biggest wire, and so the number 12 gauge wire is the smallest wire that will satisfy both requirements. Let's talk about some more things about electrical terminals and terminal strips in an aircraft. Now here's an example of a terminal strip, I believe, where you've installed different terminals here, and they're made of some dielectric material that will not conduct electricity. Basically what you're doing is putting wires on a terminal, and you want to keep these wires apart from each other. So let's take a look at what they're made out of. They're made out of paper-based phenolic compound, and you need to know that. Terminals, and let's take a look at the exact FA test question. This paper-based phenolic compound, most electrical terminal strips in an aircraft are what is known as the barrier type, and they're made of a strong paper-based phenolic compound. So you got that right there. Now, let's assume you're installing a terminal stud. What is the smallest terminal stud that is allowed? Aren't you glad you know this kind of thing? Well, the smallest terminal stud that is allowed is a number 10 stud. They want you to know that the smallest terminal stud that is allowed is a number 10. The question is, what is stacking? Well, stacking is a term commonly used when 2 or more electrical terminals are installed on a single lug. So if you put more than one terminal on a single lug, that is known as stacking, and it has nothing whatsoever to do with a brick. Never mind. All right. What is the maximum number of terminals that may be connected to any one terminal stud? Well, how much can you stack? And the answer is, how stacked can it be? Well, it can only be up to a maximum number of 4. The maximum number of terminals that can be connected to any one terminal stud is 4. All right, now let's talk about bonding wires. What are bonding wires? Bonding wires are wires to ground something, so you ground it to the airframe. What is the maximum number of bonding wires that may be attached to one terminal grounded to a flat surface? And the answer is 4. 4 seems to be a big number on this. 4 bonding wires is all you're allowed to put in one terminal. Now, the reason you install bonding jumpers is to provide an easy path for electrical current to ground. So bonding jumpers should be installed in such a manner that they provide a low electrical resistance in the ground circuit. All right, let's talk about the resistance of the current path through the aircraft. Let's assume you're grounding an electric motor or some kind of electrical device, and you're grounding it by bolting it to the aircraft. What is the resistance of the aircraft considered to be? And the answer is the resistance of the aircraft itself, the structure through the ground that this is going through the ground is considered to be negligible, provided the structure is adequately bonded. So you don't need to take into consideration the resistance of the airframe itself. It's considered to be negligible. And we're talking about the ground circuit back to the battery. Whenever you complete the circuit, you ground it to the airframe, it goes back to the battery. That's the resistance that's considered to be negligible. Let's assume you and I are installing electrical switches in an airplane. How are they rated? Well, here's an example of some electrical switches. They are rated according to voltage and current. So how are switches rated? By voltage and current. And by the way, they say you should use a D rating factor. You should actually use a D rating factor for current when selecting an electrical switch for installation in an aircraft utilizing a direct current motor. Why a D rating factor? Well, because you want to make sure that the switch can handle starting loads and those kinds of things. So the switch should be bigger than is necessary. That's what a D rating factor means. All right, now let's talk about current flowing through the coil of a solenoid-operated electrical switch. Now, we'll talk more about that later on, but a solenoid switch is an electromagnet. When you punch a button, you send an electromagnet through a coil, and that pulls down a relay. And that's a solenoid-operated electrical switch. And current will flow through that coil of that solenoid, which is an electromagnet, as long as the control circuit is complete, because what you're doing is you're holding a switch down. It's a little switch that operates a bigger switch with an electromagnet. That's what it's all about. So the question is, how long will current flow through that coil? And the answer is as long as the control circuit is complete, because it's that electromagnet, the current flowing through the coil, that holds the solenoid down. I knew I could get it out. All right, let's talk about how you install switches in an airplane. And the answer is you install switches so that on is either up, as in this case you push on the upper part of the switch, or forward. And so the FAA question about this is switches used to control engine electrical circuits should be installed so that the on position is reached by a forward or upward position. Now let's talk about electrical protective devices. What's that? Well, that's fuses and circuit breakers. Part 23 of the regulations requires that most aircraft circuits do have electrical protective devices, but not all. Here's an example of a circuit that does not have either a fuse or a circuit breaker generally, and that's a starter motor circuit. Not all of them do. If it's not going to be any particular hazard, they don't have to have it. But most do, and what they mostly have is circuit breakers. And they're installed primarily for the reason of protecting the wiring. You have them here so the wiring doesn't overheat and melt on you or cause a fire. And they're rated based on the amount of current that can be carried without overheating the wiring installation. You just don't want to overheat the installation generally. The whole idea behind these circuit protection devices is that the circuit is protected, and you do this by having the fuse blow or the circuit breaker pop before the circuit burns itself up. Now, in order for that to work, then, the time current capacities of the fuse or circuit breaker must be below those of the associated conductor. In other words, you want the fuse or circuit breaker to fail before the circuit itself burns up, and to do that, you've got to make sure that these things are less rated than the circuit itself. All right, let's take a look again at Federal Aviation Regulations. Part what? Well, Part 91 in this particular case. So Part 91 requires that if you do use fuses as an electrical protection device, one spare set of fuses or 3 spare fuses for each kind is required in the aircraft. Part 91 requires that one spare set of fuses or 3 spare fuses for each kind is required if you do use fuses. And that is going to be a test question, as you might guess. So one set of fuses, 3 spare fuses, Part 91, and it requires that if fuses are used. All right, Part 23 specifies that each resettable circuit protective device requires a manual operation to restore service. Now, what they're saying here is if you have a circuit breaker and it pops, it can't go in automatically. It requires a manual operation. You have to push it back in to restore service. And if it doesn't have to be pushed in, if it doesn't require some kind of manual action, it's not allowed on an aircraft. So the use of automatic reset circuit breakers is not allowed. Well, what are the types of circuit breakers you might have in an aircraft? Well, there's 3 basic types of circuit breakers: push-pull, push to reset, and trip-free. As you might guess, you and I are going to talk about all 3 of these. What is a push-pull one? Well, that's one that can be used as a switch as well as a circuit breaker. So a push-pull circuit breaker can be used as a switch. What is a push-to-reset type of circuit breaker? Well, it cannot be used as a switch, and you push it back in to reset. And finally, the last one we need to talk about is a trip-free trip-free circuit breaker, and that seems a little bit backward to me. The word trip-free I find confusing about this, and I always have. But that's trip-free is a type that it's impossible to manually hold the circuit breaker closed when excessive current is flowing. In other words, it'll just keep popping out and you can't hold it closed when excessive current is flowing, and that's called trip-free. And that's a good way to have it designed. Of course, you want it designed that way. It's just the word trip-free seems confusing to me.
You could physically hold it. It's just the circuit will still open. Anyway, keep going.
On that, but that's the definition of a trip-free circuit breaker. You cannot manually hold it closed when excessive current is flowing. Let's you and I talk about batteries. And the whole idea of batteries, of course, be able to start an airplane generally or operate an airplane's electrical system even when the generator isn't working. You should keep the battery fully charged. That makes sense. It's a precaution taken, of one thing, to prevent electrolyte from freezing in a lead-acid battery. So if you have a lead-acid battery, you know one of the reasons you want to keep it charged is to keep the electrolyte from freezing. All right, the generating system of an aircraft charges the battery generally inside the aircraft by using constant voltage and varying the current. So what you do is you apply a certain voltage in a 28-volt system. You might, for instance, apply a 28 volts. And when the battery is low, a lot of current will travel through the circuit. And when the battery gets charged up, the current gets less and less and less. But you're applying the same constant voltage at all times. And that's a generating system used in the aircraft. And that's called a constant voltage and varying current system. Now, there is another method of charging a battery, and particularly a NiCad battery, and that's called the constant current method of charging an NiCad battery, and that's the most effective for maintaining cell balance. And if you want cell balance, and that's important to you, and you're charging NiCad batteries, you would maintain a constant current method of charging that battery. And what you do is always have the same current flowing and vary the voltage as necessary to have that same current. So you might, on a 28-volt battery, start charging at 25 volts and the current flows at a certain level, and as you have to keep increasing the voltage to maintain that current as the battery gets charged. That's called the constant current method, and that's for bench charging, basically a NiCad battery. It's most effective for balancing the cells, maintaining cell balance. Let's talk about how batteries are rated. Batteries are rated according to ampere hours. What is ampere hours? Well, ampere hours is amps times hours. You take the output that the battery is capable of putting out, or does put out normally, and multiply it times the number of hours it could put it out, and that tells you how much energy is stored in that battery. That's really what we're talking about. So let's take a look at an example of this. Let's assume a battery had 45 amps for 2.5 hours. It could put out 45 amps for 2.5 hours. What's the ampere hour rating of the battery? All you have to do is multiply it out, take your electronic calculator, multiply 45 times 2.5, and you get to 112.5 ampere hours. All right, or they'll give you another example. Let you and I take a look at another example. We're going to have 140 ampere hours and it'll deliver 15 amps. And how long will it deliver for? Well, you have 140 ampere hours divided by 15 amps. So what you have to do is take 140 to divide by 15. And if you have a 140 ampere hour battery and it's putting out 15 amps, you divide by using your electronic calculator and it'll do this for 9.33 hours. You guys got it made. Now let's you and I talk about DC generators. You're familiar with DC generators. They're used in aircraft all the time. You know everything there is to know about DC generators, probably except for the questions the FAA is going to ask on the FAA written exam about them. So let's take a look at how they work theoretically.
This drawing's bad. All right, brief intermission, not like leaving the room, just intermission from John here. I'm going to click open on the screen, something I missed showing you our last slide. Oops, wrong slideshow. I'll get it. If you go to the very end, I'll open up the beginning. This one. This was Fridays, right, with the plane faith and Harrison's hometown. You go to the very, very end of it. Whoa, too far. What? Apparently you can't go past or shuts it off. There we go. You'll get this if you go to YouTube and look for something to that effect, whether it's power plant, airframe. There's a lot of different people that did these, and some of them are quite boring. They're just reading through. Did you guys receive the books that have like the oral questions where you can read them? So these guys basically read to you. So it's like sitting in the lunchroom with Sam Yoder and having him read to you. So I did this a bit towards the end of the year because I was a little worried about passing my test. And
Power plant reciprocating engines oral questions.
This one's not specific to electrical.
What is the purpose of dynamic dampeners on a crankshaft?
Balances it dynamically.
They reduce engine vibration.
It's close. Okay.
What types of bearings are generally found in reciprocating engines? Plain, ball, and roller types. Are the connecting rods used in each cylinder of a radial engine the same? Explain. No, radial engines use master and articulating rod assemblies.
You'll find out later. All right, we'll do one more.
Name the different types of piston rings.
Oh, yes. You got oil control, pressure control.
Oil control, compression, and oil scraper. Where should piston...
So anyway, kind of good for studying. I get sick of reading, and I'll admit I went through these like 2 or 3 times. Just listen through it. It takes forever. But that was one of the things I did getting ready for my writtens, and I think it works pretty well because they're pretty much straight up for like oral prep, but also your writtens have very similar questions. So I wanted to bring that up to you. Just point out that they're available. You don't have to do it, but it's something I use instead of using a buddy. If you're on a long drive somewhere, pop it on, listen. But, okay, I've got to get to, oh, that's why. Got to get 4130 of Mr. King. Say, oh, why does it say typing?
Is this all we're doing for reviews, watching this?
No, I got some other review. About close.
Aircraft, one way or the other, the way you generate electricity is by taking
When I did it on my computer, oh, that's what it was. All right, don't take me now. We'll just go fast. We got to get through all his, he doesn't explain this very well. So that drawing he's going over right there, you guys have the new one with the numbers on it. And I would recommend making sure you know what's going on, because there's some questions on that. Skipping the ignition stuff, because we'll do that in ignition class. Boy, I hope I time this right. What? All right, I gotta back up. We'll get it. We just gotta catch the last like 5 minutes, 10 minutes. Okay.
here on the bus bar. Now, in a normal start sequence, the next to the fuel valve,
We'll catch this one. We'll see how he does. I think that might be where I need to be.
First of all, you need to know that there are 2 ways to get power to the main bus. Here's the main bus up here, and one way is through this battery, and that's one heck of a battery, as you can see by looking at it there. And what happens is you close the battery switch, and that creates a path of current all the way here to this ground through this battery solenoid, and it closes this solenoid, and that gives you a path all the way up here to the main bus. So you can just get power to it through the battery switch right here, and that's one way to do it. The other way to get power to the main main bus is instead you go up here to the external power connector. So you plug in the external power connector or an external power receptacle, and then power will go all the way, if you follow this, up to the main bus this way, and now that's the other way to get power to the main bus. Now let me ask you a question. Can you get power to the main bus from the battery and the external power source simultaneously, both at the same time? Well, it's generally not a good idea. So what they did is they installed a switch right here called the external power receptacle switch. And what that is a mechanical switch. When you plug in the external power cord, it opens that switch, thereby breaking the circuit to the battery solenoid and opening the battery solenoid. So now you don't have power all the way to the ground from the battery solenoid, and you cannot get power from the battery at the same time. So one of the questions they're going to ask you about this is this type of system depicted capable of operating with either the battery or an external power source? And we showed, yeah, you could either do it with the battery or external power source, but how about both at the same time? And the answer is no, because you have this external power receptacle switch that automatically opens the circuit and lets the solenoid open, and thereby interrupting the battery circuit, so you can't get power from both at the same time. Now, let's assume that the battery switch is on. We've got the battery switch on. What we've done then is close this solenoid, and we've allowed current to flow all the way up here to the bus power. So now we have bus bar. So we have power up here on the bus bar. Now, in a normal start sequence, the next thing you're going to do is close the engine master switch, and that will send power to the fuel valves and also power to line 12. Let's follow line 12 and see where it goes, and that'll take power and give it to all the way to the power lever switch. So now you've got power to the power lever switch, and you've got power to the fuel valves at this particular point. Next thing you would do is, as a pilot, you would reach forward and depress the start switch. You're going to depress it and release it. You aren't going to hold it in. We'll talk about that later on. But when you do that, current then energizes both the ignition solenoid wire, which is wire 10. So let's take a look at that. You've pressed the start switch and up here, and wire 10 is energized, and it goes all the way through the ignition solenoid. And what it does is it pulls this solenoid up and gives you a path that you'll use later on all the way to the igniters. Now, you're not using that path yet because you haven't advanced the power levers and you haven't closed this circuit right here. But you've now got power right here up to the igniters, except for the fact you need to close this. So what you've done is made power available to the igniters in a sense. Also, the other thing you've done when you close the engine start switch is you energize this circuit right here, which is wire 8, which goes right here to this ground, and in the process it pulls this starter solenoid down, and that completes the circuit to the starter motor. And of course, as it goes to the starter motor, it goes all the way down here, and the starter motor starts turning. So now we've got energy to the starter motor. Now, once the starter solenoid is energized, current flows through here, we've got the starter motor turning, and we're on our way. Now, if at this point the engine fails to rotate when you depress the starter switch, you have got a problem. And the most likely cause of that problem is the starter solenoid didn't work. It's kind of mechanical. It has to move. And if that didn't move, then the engine doesn't rotate because the starter doesn't work. So if you do this and the starter doesn't rotate, that's probably the problem. The starter solenoid didn't work right. Now, at this point, you've got the engine rotating, and you've got power to the fuel valves. You've got the ignition enabled but not operating yet. So the next thing you're going to do in the start sequence is you're going to advance the power levers. So when you advance the power levers, here is what happens. So let's take a look at that. Up here, first of all, you advance the power levers, you close this power lever switch, and now you send electricity all the way through this power lever relay to ground, and that pulls this relay down and closes all of these switches. And when you do that, you send power to the fuel pumps. So now you got fuel, and now you've closed that last switch all the way down to the igniters, because remember, this ignition solenoid closed earlier, and so now we have fuel to the engines and we have igniters going. So we are probably going to have a light off pretty soon here. So we've got that the circuit already completed now to the igniters. Now they're going to ask you some questions about this. They're going to say, okay, let's assume you've placed the engine master switch and the battery switch in the on position, and you advance the power levers. Where do you send fuel, or where do you send electricity at this point? Well, you send it to the fuel valve. We already talked about that earlier. You send it to the power lever switch, which is right down here. The power lever relay coil, which is we have already talked about here, and the fuel pumps, and in one ignition contactor. So all of that happens when you move those switches forward, the power levers forward. Now let's take a look at another thing that happens when the starter motor starts turning. It starts pulling power. Let's take a look at what happens when it pulls power. It pulls power through the undercurrent solenoid, and it'll close the undercurrent solenoid. Now when that undercurrent solenoid is closed, what you've done is created another path for the starter solenoid. The first path of the starter solenoid here is wire 8. But when you close the undercurrent relay or solenoid, now another path goes to the starter solenoid to keep it closed. So if wire 8 at this point became broken, no big deal, because you have a separate path to the starter solenoid. And of course the power from the starter solenoid goes through here right to the starter. So now you kept the starter energized even if something happens with wire 8, it got broken. Why do they create that second path? So that you can just press on the start button and release it. Because you normally do that, just depress it and release it, and as soon as the starter starts turning, it creates a path of electricity here that pulls the undercurrent solenoid down and creates the second path to the starter solenoid, and thereby you don't need wire 8. So
Do we need wire 8? What do we need wire 8 for still? Our igniter. So if we were to break wire 8 right now, we wouldn't have power back feeding down to our igniter. So we do still need wire 8, but he's trying to make the point that we don't need wire 8 to keep the starter running, but we would need wire 8 to keep the igniter igniting until it ignites.
at this point wire 8 got broken or something, it wouldn't make any difference because it's no problem at all. You don't need it. Now this stop relay up here is normally closed, so you normally have a path all the way through when this happens, and that's what we have right now. But there is a case in which you would like to have that relay become open. In that case is when you get a hung start. If you get a hung start, what happens is the engine fails to reach sufficient speed and it'll never get going fast enough where it'll start and run on its own. Well, in that case you want to terminate the start, and you would do that by depressing the stop switch, the start-stop switch. And you're going to depress on that, and that'll energize this wire all the way up here, so it's wire 16 all the way up to the stop relay, and open the circuit and interrupt that path to the starter solenoid. And now you'll stop the start. It's hard to say stop the start, but you'll terminate the start right at that point. And that's what the point of that is. And you would depress that switch if you had a hung start. Now we said this undercurrent solenoid provides a path of electricity through wire 5 to the starter solenoid, but it has another purpose, and that is when the engine starts to run on its own, the starter motor will pull less current. And as it pulls less current, it will not have enough current to keep the solenoid closed, and the solenoid will pop open. It's spring-loaded, and what's going to happen now is that'll shut off your starter motor. And that is how the start is normally terminated, and that's a normal start, so that's why it's so automatic. As soon as it's up to speed, you don't have enough current to close this solenoid, it opens and the start is terminated right there. So that's an automatic termination of the start. It's a good thing. So we now have this engine running and started, and we're going. We've got the start terminated and the engine's running on its own. Now let's take a look at some other things they're going to ask you about this. First of all, let's assume that power is already supplied to the bus bar. We got that. And we've closed the engine master, so we closed the engine master, and that sends power to the power lever switch. We've got power all the way now to here to the power lever switch. Now we close the power lever switch, and how do you do that? By advancing the power levers inside the aircraft, and that allows current to go through the power relay, the power lever relay, and that's going to pull down the power lever relay and close all these switches and send current to wire 14, and if you had the test switch closed, to wire 15. Now they're going to ask you a question. They're going to say, what would happen if wire 14 or wire 15 were broken? Well, if wire 14 or 15 were broken, the igniters would work normally through the normal operation, because we haven't broken that circuit. We got this circuit that we talked about all the way to the igniters, but we wouldn't be able to test. So if wire 14 or 15 were broken, the igniters would operate normally, but would not work when tested. So you have the levers forward and you're trying to test igniters, it wouldn't work. If on the other hand wire 10 were broken, that's the wire down here to the ignition solenoid, or the ignition solenoid itself were broken, they're going to ask you what would happen, and the answer is the test would work, but you couldn't get power to the igniters during a normal start attempt. So it wouldn't work during a normal start, but would work during the test. Now let's take a look at one more question they're going to ask you about this test switch. And of course the purpose of this test switch is to be able to test the igniters in the aircraft. And they're going to say, okay, let's assume you're sitting in the aircraft and you have power applied to the bus bar. So you got power up here. Then what switch changes would you have to make to allow the ignition exciter's test switch to function? Well, the first change you'd have to make from that point on is to turn on the engine master switch. When you've done that, now you're going to send power through line 12 or wire 12 all the way to the power lever switch. Now you got power to that point. And then from that point, what you need to do is close the power lever switch, and that will pull down the power lever relay, and that will get you power all the way to, if you follow down here, 11 and 14, and down to the test switch. So the changes you would need to make once you have power to the bus are you would need to close the engine master, and then you would need to bring the power levers forward. Well, that is figure 5, and that's all there is to it. I hope you had fun with it, and that's all the questions they're going to ask you about this on the test. Let's you and I take a good look at magnetos. Boy, I'll tell you what, magnetos are one of these.
Oh, I'll save that one for the next class. All right, let's take a little break. Come on back. We're just going to make a short break. We'll get you the lab. So coming back at 20 after, stretch your legs. And we'll see you shortly. Nope, not today.
It's gonna help you heal faster.
The entire electric.
Yeah, you walk away crippled. Yeah, look at your knee, bro. I did that too. You was like, oh, I'm a dirt bike. I fell on gravel. Yeah, that was actually me. I kicked my knee, bro.
System. But most well, it's time for you and I to take off and get out of here because, believe it or not, we engine combination. It means the pawls are recon. And also, so that if the starter motor is going fast, it's called a shear point, so it'll just almost a fusible drive shaft, so it breaks instead of tearing something else up. Now, sometimes you might hear a clicking going in there. You want speed because the starter were overspeed at a certain given end too. It's going to be too fast for the starter. So you do need to make sure you don't have the starter go too fast. Or something like that. You could also close it manually. Reciprocating ignition system, but it is with a turbine ignition system. So you want to follow a procedure to make sure that you do not get a lethal shock if you are working on or removing a turbine engine igniter plug. Here's the procedure you want to follow. First of all, turn off the ignition switch. That's a good idea. You don't want to get shocked. 2, disconnect the lead from the plug. And finally, ground the center electrode to the engine, and you follow that procedure to make sure that you will not get a fatal shock when removing a turbine engine igniter plug. You know, when you take a good close look at a turbine engine like this on, say, a Boeing 747,
All right, we're going to get going again. When I did this on the computer to get us going, I had my numbers to go off, and they're not showing up on the screen. So we're going to give a quick, I think it's the 5 or 10 minutes. He goes over starters, and he does it in a fairly good way. Remember, this is a review. You're not learning anything new, but hopefully it just cements it in for you, and then we'll do our review. So a little bit more, John, please.
and the way this is, one of the things that comes to your mind is boy, that is a big engine, and there is a tremendous amount of mass rotating there. And one of the questions that has to come to your mind is, how do you get all of that started? How do you get that mass rotating? Well, the answer is it's going to take a lot of power to get a big jet engine started like that, and you don't want a lot of weight, so you use pneumatic starters or air turbine starters to start these engines. And the primary advantage of a pneumatic air turbine starter over a comparable, we'll say, electric starter for a turbine engine is a high power to weight ratio. You can get tremendous power out of a turbine starter or a pneumatic starter with very little weight, and that's the reason you do that. That's how it's done so efficiently. And normally, you need a lot of torque when you're first starting that starter, so you have a big wheel on the starter, and the air comes in at the outside of that big turbine wheel on the starter, and it turns that, and that's called, first of all, we're talking about an airflow impingement system, how that air impinges on the turbine in that starter motor, and it comes in at the outside and hits that and gives it a lot of leverage, because if you're hitting on the outside of the wheel, there's a lot of leverage there, and then it goes inward, so it's called a radial inward turbine flow, or radial inward flow turbine, and that's for a low pressure starter. Very little, less low air pressure, and you use this wheel and come in from the outside of the wheel, go inward. Now, an axial flow turbine is used on a high pressure starter, and it doesn't have as much torque, and so therefore they can get away with that because they have high pressure. So if you're using a low pressure starter motor, normally they'll have a big turbine wheel, and the air comes from the outside and goes to the inside. It's called a radial inward flow turbine. I bet that's more than you wanted to know about pneumatic turbines. By the way, low pressure starters we talked about use a high volume of air but low pressure. Now, what are they talking about when they're talking about low pressure? Well, we're talking about 40 40 psi, so that's reasonably low pressure, but we're talking about 50 to 100 pounds a minute, so that's a high volume of air, and unfortunately, you need to know these numbers on a test, 40 psi and about 50 to 100 pounds a minute, and it's supplied either by an APU or a ground power unit, or maybe bleed air from an operating engine. So the air source for these pneumatic starters for these big turbine engines comes generally from a bleed air or a ground power unit or an APU unit. Now, you want to have some way of regulating this, so they have what is known as the starter pressure regulating and shut-off valve. And it's a valve that turns on and off the air supply to that pneumatic starter motor, and it's normally open and closed pneumatically. Now, if you had a lot of corrosion or icing or something like that, you could also close it manually, and you'd use a great big handle to do that. But normally they operate pneumatically with a manual backup. Now, if you do need to use the manual backup to operate the pneumatic start valve, then you've got to make sure that you shut off the starter when it reaches a certain RPM, because you can actually damage the starter. So the starter T handle, which is the manual way of operating it, must be closed at the scheduled starter dropout speed, because the starter will overspeed at a certain given N2. It's going to be too fast for the starter. So you do need to make sure you don't have the starter go too fast. Now, there are a couple ways that the starter, if it's operating normally, will control itself. Now, there's two ways to prevent starter motor overspeed. You got this little turbine starter just going like the devil, and you don't want it to overspeed. So one way you could do it is you could have what is known as a flyweight cutout switch, and it's just a switch when it gets too much speed, it'll just cut out the air to it, and it basically cuts out the airflow to the pneumatic starter, and it prevents a starter overspeed by activating that flyweight cutout switch. Now, the other way you could do it is you could have a starter design, and what you have is some kind of design so that the air gets to a maximum speed and can't go any faster, and you use the speed of sound. What you can do is you can choke the air off. Anytime the air goes through a constriction like a venturi and it reaches the speed of sound, the air cannot go any faster, and it chokes it off. Sometimes you can design the stator nozzle system on a pneumatic motor for the air going into the turbine would have to go through the stator nozzle, and it chokes it off when it hits the speed of sound, and it prevents the starter from reaching burst speed. So it's just an aerodynamic design inside that pneumatic starter that keeps it from overspeeding. So two ways of doing it, flyweight cutout switch or an aerodynamic design so that it chokes the airflow. It's called choking the airflow when it gets to be supersonic, and it just prevents it going from any faster. And if the inlet air does not terminate on schedule, that's why you would have to do that. So let's assume that for some reason the start valve didn't work and the air keeps going in there. You want something to keep it from flying apart and overspeeding, and having a design that chokes the airflow is one way to do it. You'll see those magic words on the test. Now, another thing you can do to kind of protect this pneumatic motor is have what is known as a drive shaft shear point. And that's another safety feature that you can put in a pneumatic starter in case the clutch doesn't release from the engine at the proper time. What's going to happen is that you'll have some weak spot in the drive shaft, that's called a shear point, so it'll just almost a fusible drive shaft, so it breaks instead of tearing something else up. Now, sometimes you might hear a clicking sound at the engine coast down in a pneumatic starter, and you're wondering why that is. Well, sometimes they incorporate a sprag clutch, which is just a freewheeling clutch, so that if the starter motor is going faster than the engine, it engages, otherwise it disengages. And this has little pawls that contact on the ratchet gear. And sometimes they don't pull in properly. Those little pawls little kind of fingers don't pull in properly, and so if you hear a clicking sound on a pneumatic motor engine combination, it means the pawls are recontacting and are riding on the ratchet gear. That's a bad sign, but that's the cause of that clicking sound. Now, let's assume you want to inspect a pneumatic starter. Well, one of the things that's going to be involved inspecting the pneumatic starter is checking the oil level of the pneumatic motor. That turbine motor goes like the devil. It has lots of power to it, so you want to check the oil level on it. And also, there's a magnetic drain plug, and you check that drain plug, see if there's any little metal filings. And those are the two big things about inspecting them. They're pretty simple. The inspections involve checking the oil and checking the drain plug for filings. Well, it's time for you and I to take off and get out of here, because believe it or not, we've wrapped up ignition, electrical, and starting systems, and we've had a lot of fun, and we've done some things together that I know that you'll remember for a long time, because who can forget those starting system circuit schematics we went through?
All right. so I don't have enough for everybody. So we're just gonna do one side of the room versus the other side of the room. And I think there's 20 is all. So if you raise your hand, you get it correct, you get a point, your team. If you raise your hand, you get it incorrect, minus a point. So we're just gonna do a little bit of review and go from there. Quick review, that one's just not a question, but our frequency triangle, freak triangle as I like to call it. Frequency times 120 is on top of RPM and number of alternator poles. There might be a question on the end, but just one more review on there. Okay, here we go. One more slide. There it is. What is used to convert AC current into DC current on a power generating device that has a spinning armature? Parker. Commutator is correct. Good job. One for your side of the room. Very good. Good. Okay, here we go. What is used to convert AC power to DC power in a generating device that uses a stationary armature? A hand. I see that hand. Diode bridge. Yeah. What's another word for the diode bridge? Rectifier. That's right. Diode bridge or rectifier. Very nice. You might even just say diodes or a diode, but any of those. Yep, you're in the neighborhood. Okay. When is current higher in DC motor? When it's starting or when it's full speed? Corbin, I saw your hand first. When it's starting, that's right. Why? Anybody? Why? This is a point question. Why is it highest when it's starting? Because it's getting up to speed. You think it's slower then, right? A car uses more gas once it's at a high speed. Why is an electric motor different?
Uses more energy to turn it over.
So it all goes back to when we're at a slow speed or not moving, we don't have wires cutting magnetic field. So the amperage through that wire basically is only held back by the resistance of the wire. Once the motor's up to speed, we now have a wire with current, and that current is cutting a magnetic field that's there, and the direction, the math, you end up switching from your left-hand rule to your right-hand rule, and it produces that back EMF. So even though we're putting electricity through the wire to try to get it to spin, once it's actually spinning, the motion of it spinning causes a backwards EMF, or it's actually fighting the voltage. So the faster it goes, the more back EMF there is, and that's what ultimately kind of limits our motor speed. There's some geometry too, but so once it's up to speed, the amp draw actually starts dropping down because of back EMF. Lenz's law has something to do with that. What is varied to control the output voltage of a generator? I'm going to go with Leo just because I saw Yoder once before, but you know, we'll see what happens.
The field input?
Field input. What, like zeros and ones? Field, what do you mean?
From the
What's,
voltage
what are,
regulator, that,
yeah, what are you inputting?
um,
Air pressure?
voltage.
Voltage, yeah, so that's right. So the field input, yep. So we're gonna vary the field input. I like that answer, and field input is the voltage to the field. Now, sometimes we have a grounded field, right? And like in the, oh shoot, might be a question coming up. Most our generators with the vibrating points are grounded. So when we say we're changing our field input, we might be doing it, I'm gonna call it on the back side of the field, on its heading to ground instead of the front side. But yeah, the field input, or the voltage to the field is the correct answer. What controls the frequency output of an APU alternator? Interesting question here. Yoder, you had your hand up. Constant speed drive. Oh, that's incorrect. Anybody else want to take that one? Elijah. RPM. Can you elaborate? What controls the RPM then? the RPM controls the frequency, which it does.
Well, don't we set our APU at a set speed?
Yeah, there you go. So we got it back. So an APU usually doesn't have a constant speed drive. A constant speed drive is a hydraulic thing typically that will take a hydraulic or pressure and it'll run our alternator at exactly the right speed. An APU, instead of a constant speed drive, actually has the controller on the APU is a speed control, not with the same name. We don't call it a constant speed drive. It's just it's going to be the fuel metering and everything on the APU. So
That's varied by the load.
they will run to hit this RPM and whatever the RPM is. So if we need more or less electrical power out of our APU, then they'll vary the field to the alternator on the APU. But the frequency, basically APU runs at one speed and that sets the frequency. So the next question is, what controls the speed of an alternator on a jet turbine engine? These guys on the left side of the classroom are a little, we're gonna have to start doing like Bible drills where it's like charge, go, to give Yoder a second guess. Okay, Yoder, yup, nobody else raised their hand.
ESD?
What?
Is this the constant
This
speed
is the
drive?
constant speed drive, yeah. So on a jet turbine engine, they do have a constant speed drive that varies the alternator speed. Yeah, so that was the one he thought he was getting. Yup. And that's why, remember that bus diagram we had? It said you can vary the speed of the alternators on all your turbine engines because they have constant speed drive balancers to get the frequency the same, but you can't match an APU typically with a turbine engine because the APU is controlled by the APU speed and we can't fine tune that quite as much as our constant speed drives. Go ahead.
Can you just explain that a little more? How is it constant speed drive?
Find a picture. A constant speed drive is typically a hydraulic pump feature, like a hydraulic motor, and it will get to adjust the, I'm gonna use the word the swash plate, so that we get exactly the right frequency, and then they can even fine tune it so that, I'm gonna call it inside that frequency, we get the same voltage points on the timeline, voltage humps between all the engines. So not only will they get exactly the right frequency, but they'll also align the voltage curves on top of each other. An APU, we can't really fine tune that much. They might be able to get the right frequency, but our voltage curves probably won't line up right on top of each other. So we say, we can't really tune in an APU to a turbine engine. It's just not as high tuned. Now, we're a handful of years after when a lot of these questions were written. There might be some APUs in aircraft that are able to do it. If they are, they actually probably have a CSD, a constant speed drive, on the APU between it and the alternator. So like a big old Boeing or big old Airbus, they might do a constant speed drive inside that APU, but that's not how the prep work questions are written. So most stuff doesn't work that way. Does that make sense? In turbine class, I think you get to run an APU even. That's kind of fun. But basically you start it up, there's no throttle, you don't control anything, because it'll run up to its speed and it just sits there at its speed. Alright, what does flashing the field on a generator mean? Why might you need to do it, Sydney? Yeah, did you see this question before it popped up? Yeah, that's okay. Restore the residual magnetism.
Are you reading ahead?
She saw it pop up when I was a little bit ahead. She's seeing what's coming down the road. Yeah, restore the residual magnetism. Usually that's only if you have the thing tore apart, right? How do you do it, Sydney? Picking on you.
Don't you put it on the arm and then before the reverse current?
Yeah, basically, so it's bat and arm on the 3-position thing. Basically, all we need to do is we need to get our battery voltage over to the arm terminal on the pick Parker. You're doing great, Yoder. You're doing great.
Just kind of deal.
What? Full field, what would that do? If we full field a generator, what's gonna happen, most likely? Like, is that a problem? It's like, whoa. Or is it like, ah, no big deal?
Motorize it?
Not so much motorize it. We'll check with John.
Won't the voltage output decrease?
Voltage output would increase. So basically, as we full field alternator that doesn't need to be full, or generator that doesn't need to be full fielded, we're saying, give me more, give me more, give me more. And it's gonna give you more, which means our voltage is gonna go up and up and up. And if the voltage goes up, well, your amp draw is probably gonna go up, so probably either gonna burn stuff out, or hopefully our over voltage regulator at that point would kick in and say, whoa, that's too much. We got too much going. The initial question I did get. Come on, left side of the room. Got a couple more. We're getting close though. Do electrons flow into or out of the positive terminal of a battery when it's charging? It's a tricky one. Did Gavin raise his hand? Yes? Oh, I missed it. Gavin? Into, okay, let me think through that one. Plus, minus. So, do electrons, oh, so I messed with you and said electrons. So we've got to be electron theory. They flow into or out of the positive terminal belt when it's charging. So we know charge is going that way, so our holes, if you will, would be going in. Electron theory is reversed, so electrons would actually flow out of the positive terminal
But you're a conventional guy.
when it's charged. I am a conventional guy.
It's a prep work question,
So I looked at the prepware one. So if you look at that, you got to be thinking, did they say electron theory or conventional theory? You got to stop and make sure and go, wait a minute, what they just say there? Am I forward? Am I backwards? Am I electron theory or conventional theory? So you do got to stop and think about it. Everybody making sense? Okay. Conventional guys, we don't follow electrons through. We follow holes around because we didn't know about electrons for a while. All right. What will a state of charge meter show when a generator is charging the battery?
Positive.
Positive. That's one for the left side of the room. That's right.
We are talking physical.
What is it? Well, where is the state of charge meter located? Ooh, I saw Leo's hand.
The battery in the bus.
State of charge is between the battery and the bus. That's right. He beat you.
Between the alternator and the bus.
Okay, alternator and bus, and or generator if it's a generator system. Yeah, all right. Sorry, well, we'll answer this one, then we'll go back. David.
On is forward and upward.
Forward and upward. So I was reading through the prep, that's correct. I was reading the prepware questions, and I was like, oh, that's an easy way to think of it, and they kind of mentioned it in the movie. The electrical switches, and technically they're saying the electrical switches that control the engine, we are in a power plant after all, but electrical switches that control the engine, they should be mounted just like all the other engine controls. And I was like, okay, that helps me remember it too. So when I push the throttle to go fast, I'm pushing forward. Same with the fuel. If I want fuel to the engine, I push forward. And you could kind of say upward is similar. I don't know if I have a lot of throttles that go up and down, but that one's back to when I fall on an electrical switch, I want to turn it off. So forward is the correct way because forward is on and we want to go fast, where to aft would be off, or I want to go back slow, turn it off.
Can you discover what direction that is if it's mounted on the ceiling?
If it's on an angle on the ceiling, yeah. Most of the time, if it's on the ceiling, we're forward. Now, as as our ceiling gets tipped further and further and further, but yeah, typically ceiling you're gonna consider forward is on. But, yeah, it gets a little fuzzy in there, right? Yeah, it does get a little fuzzy. All right, did somebody have a question on that load meter one?
I like the state of charge between a negative and positive.
State of charge is the one that's telling us, are we using the battery or not? So state of charge is gonna be between the battery and the bus to say, what's going on with our battery? Because it's a state of charge of the battery. Where a load meter is how much load is on our generating system. So that one will be between the generator or alternator and the bus. All right. Oh, shoot. I know, they're all, you know, who, did I not call anybody on this side yet? Brian,
Size 10.
size 10. We'll give you back up. You know what decimals, not, well, decimal, what fractional size that would be? Fractional size is size 10? I had to look it up. It's a 3, it's basically a 3/16. So like -3. So now if you're the manufacturer of a component or a part, sometimes you see smaller, right? But that's the number they want. It's also, just for reminder, it's also the size AWG wire connection where we switch back and forth between insulated or non-insulated. So if you can remember 10, you get both answers correct. Insulated, non-insulated, and also that wire, or the stud size. Okay, I don't think we have time to catch up at this point, but we'll do the last one questions. Ooh! Oh, Kuvar.
Prevent oxidization.
What's oxidization?
That's corrosion.
Yeah. So it doesn't help it conduct electricity, but helps prevent corrosion. Yep. And the movie said silver. I was like, ooh, that'd be really expensive. Tin is usually, I think they had one other one, but. I don't like this question, but I'm asking it anyway. I'm gonna go with Parker. I haven't called on Parker yet.
Yes, my brother.
Wire gauge, yeah. They like to ask the question. This is my next slide. They like to ask the question, what do you use? And one of their options is a dial caliper. And I'm like,
But the insulation, you know, could be.
I've been teaching them all year to use a dial caliper. And the problem is, inside that question, they're thinking it's a solid piece of wire. And we use braided wire, so we've got to pull an individual one out. Now, technically, you'd pull an individual one out and still use your wire gauge thing, is where they're going with that. So when you see that question, that's what pops up. Okay, while I'm passing the candy around, we're going to do just a couple to this side of the room. Let's see, I'm going to start in the back corner because they answered more questions back here. Well, there you go, pick one, pass it around. So here's what we're going to do. We're going to do a little tell me something Barb doesn't know. And we'll see how it works. I think we only did this once. I don't know if we did. So I'm going to take some volunteers. Tell me something Barb doesn't know about this. Anybody, raise your hand. We'll call on you. Tell me something Barb doesn't know.
That is spring that goes and like disengages once the engine is up.
It is.
And
So
it can be oversized that with that efficacy.
yeah, so it's in a starter. It's a spring that disengages, and realistically, when you go to spin it, when the starter spins, it's like a Chinese finger trap, and it engages when it spins, and it'll disengage up to speed. Good job, Brian. Good job. Nice. Barb doesn't know that. And I don't mean that in a bad way. It's just, I love the game. Okay, let's see here. I'm gonna go with this guy. Here, pick somebody that hasn't answered too many questions yet. Tell me something Barb doesn't know. Corbin. It what do you mean it's stuck?
It's not fully retracted.
It's not fully retracted, so elaborate on that for me, what even retracted or stuck, what does it do?
Well, when you spin it up, it's going, because it's inertia, it's on a, very light thread. As you spin it, it's going to stay in place, so it's spinning down on the thread. Then once it's caught up to the thrust motor, it'll retract back in because it's got a thread that's going down.
Okay, good, yup, good job. And this is why I say, tell me something Barb doesn't know, grab a friend, you do it, grab some of these. That's very similar to what you might get on your practicals with a DME. He might say, hey, how does this thing work? All right, this little guy with a wire hanging out of him, right here. Tell me something Barb doesn't know about the guy with the wire hanging out. Oh, capacitor? Oh, okay. What's that? Why do we have a capacitor in here?
Smooth it out even more.
This is off an alternator.
Smooth it out even more so it's not as bumpy too.
Thanks,
Yeah.
Oh, he got a little help. All right, I'm gonna need two more is all. Two more. Here's a fun one. These are fun because Barb doesn't know a lot about these. It's a starter, okay? Anybody else?
Got a pull cable to engage it.
A pull cable to engage it. It's gonna pull on this. Oh, cool. So it like pops out. All right, what else? Oh, how does it start the current? Oh, by pushing in that button there. Yeah, the button pushes in and that
Series wound.
close. Ooh, very nice. It's a series wound motor. That's nice. That's nice. Okay. How about this little thing on the end here? Anybody? Oh, a sprag clutch. Yeah, prevents it. Very nice. All right. And last one. Let's see, where was I going? I'll go with this. Oh, I got a horseshoe or something. Diode bridge. What's a diode bridge?
It's a rectifier.
You use an awful big word.
Converts alternating current to direct current.
Oh, that's pretty cool. How does it do that?
The diode is checked off basically, so they only go out in one direction.
Cool. All right, you guys get the idea. Instead of just studying boring books, if you get done with your labs and you don't want to do some of my extra stuff, you can play a little tell me something Barb doesn't know with your friends, with our starting equipment, stuff like that. You make sure they're telling you the straight story. But I think you'll find the exam should be fairly easy and straightforward after what we've taught and the review we've done and going forward. So that's all we got today. We'll see you for an exam tomorrow, and